one that I like. So here is a function of 3 variables, which is allowed. Actually, it's unlimited what you've got. And this one's going to be written in that format. And let's just find that one. Now, it's actually going to be a chain rule. Isn't this the log or something? So we know when you differentiate a log, you get 1 over that something. And then you multiply by that guy. And the derivative of all of this on the bottom is actually just 6. So you've got 6 over x plus 6y plus 9z. And that's pretty much it. If you wanted to evaluate this partial derivative at a particular value, like 1, 2, 3, right? So if they phrase the question, I know it's a little bit clunky, but do you get the gist of what they want you to do? They want you to find the value of this partial derivative when x is 1, y is 2, and z is 3. You could go 6, 1 plus 2 lots of that, plus 3 lots of that, and that'd be 39, 40, 6 over 40, and always simplify down, and you get 3/20. Are we cool with that? I'm just zooming through it because I think it's just practice, right? What about taking a function that has got a product rule in it? How about, this is just my version, how about z equals x e to the y over x? So 2 partial derivatives, that one, which is going to be quite messy, and this one, which is actually going to be dead easy. If you see x's in 2 locations, think product rule. If you see a fraction where you have x's on the top and x's on the bottom, then think of quotient rule, right? That's just the basic rules of differentiation. So far, so good. So would you agree this is 2 things multiplied, so it falls into the product rule world. So f dash g plus f of g dashed. Okay, and remember that these derivatives are only with respect to x. So you differentiate this with respect to x, you get 1. You leave that alone. And then you leave this guy alone. And now I'm going to mute someone because they're very noisy at turning over bits of paper. There we go. Right, now back to what I was saying. You are going to have to differentiate this fella here with respect to x. Well, when you differentiate e to a function, you get e to the function, but then don't you finish with the derivative of this guy, right? With respect to x. And y over x, although it seems, and it is, relatively speaking, very simple, you can make a mistake on its derivative if you're not careful. What is the derivative of y over x with respect to x?
That would be negative y over x squared.
Agreed. Now, if you find it a little bit tricky to see that, here is a kind of long-winded way of rewriting it. Would you agree that it's the same thing as that? Right? And now if I use the power rule on that, you multiply by the power, and then you reduce the power by 1, and then you just tidy things up. Are you comfortable now about why it's negative y over x squared? But you see, a little darn thing like that could cause you an awful lot of grief, couldn't it? You know, if you weren't differentiating, right? So this guy here ends up being negative y over x squared e to the y over x. And that is not style points. It can be made pretty, or at least prettier. This x partially cancels with that one, and now you're left with this guy. And I would say that since this is a nice common factor, I think it is reasonable that you should pull it out. So to me, that would be what I call style points. That's the nicest version of the answer, right? Algebraically, the nicest looking version. Are we cool with that one? Now, same guy, Actually, I'll rewrite him up here. This guy. But with respect to y. This is not a product rule. It's just one place that's got a y in it. When I differentiate this, I'm going to get x e to the y over x. I'm also going to get the derivative, because it is a chain rule, of y over x. What is the derivative of y over x with respect to y now?
1 over x.
Just 1 over x. Would you agree that this one cancels out really nicely and you just get that? Right. There's your style points for that
nice
one.
And pretty.
Nice and pretty. I agree. I like pretty. We're good so far? As I say, I'm just randomly going and saying, oh, that looks interesting, that doesn't. Okay. Now I'm going to show you a guy that you haven't seen before, because I think we've probably done enough of those, or at least as many as I have time for. I'm sure you've heard this term before, but what you haven't seen is how it applies to partial derivatives. Sometimes the information that you're given about the function isn't going to be f of xy equals a function or z equals a function, right? It's going to be a jumbled up versions of x, y's, and z. So it might be x squared plus y squared plus z squared equals, oh, I don't know, 9. Does anybody actually know what that shape would look like in 3 dimensions? It's a surface of something. What do you think it's the surface of?
Would it be a sphere?
Yes.
With
Of
a radius
radius?
of 9? Oh,
No.
I mean with a radius of 3?
Yes. So it would be basically a sphere in 3D space. Now, if you wanted to find the partial derivative, there's 3 of them, but the partial derivatives, we always assume that z is the major function and x and y are the random variables, right? Now, I could try and rearrange that and get it in terms of z equals. It would be messy, but doable, but it would also have a plus and minus square root in it, which is not very pretty and adds to the problem of you're not quite sure which is the right answer. So in implicit differentiation, if you're being asked to say, find this guy, for instance, what you do is you take the partial derivative with respect to x of both sides. And this is called implicit differentiation. Now, the partial derivative of any number or any constant, like x or y squared on its own, isn't that 0? Now, the partial derivative of x squared with respect to x is 2x. The partial derivative of y squared with respect to x. What's that? The partial derivative of y squared with respect.
That would be 0 because y is being treated like a constant.
Right. Now, you might think that z squared is also going to be treated as a constant, and therefore its derivative would be 0, but that's not true. Z is a special case. Z is considered to be a function of x's and y's, right? Z is the major function, x and y are the variables, right? So since it's considered as a function of x, this fella becomes a chain rule. You get 2z times dz by dx. Does that look a bit like a way back in Calc 1? The derivative of y squared was 2y dy by dx. You remember you did that? That was implicit differentiation way back in Calc 1, right? Now you might say, great, well, what do I have? Well, let's see what you've got. You've got 2x, 2z, dz by dx, and the whole thing equals 0. And we're being asked to find that partial derivative. Where do you think I'd go next? I want to find out what dz by dx is. What do you think I should do next?
You would subtract the 2x from each side and then divide by the 2z.
Well, yeah, you would do subtract the 2x and then you would divide by 2z, not 2z. You've got to learn to speak properly. 2z. And then you can't, you know I'm giving you a hard time here, Sally, right?
Yeah.
Okay.
Yeah.
So it's dz by dx. I would cancel that down, and hey, you got your answer. Do you see how implicit differentiation works in the context of partial derivatives? Right, let's try an uglier version of that. This one is straight out, because I'm looking at it, it's a version of 13. E to the 4z is equal to x, y, z. Now, this guy is implicit differentiation. How do I know it? Because their x, y's, and z's all jumbled up. It's also on steroids. This is ugly. And this, there are lots of places to go wrong. So you have to be thinking cap on, take it careful. First thing I'm going to do is, well, let's assume they want d by dx again, right? So partial derivative with respect to x, right? That's good. Here's our first problem. That guy is not 0. If it was e to the 4y, it would be 0, right? But if it was e to the 4x, it obviously wouldn't be 0, but it's e to the 4z, and it's still not 0. Now, if you differentiate e to the 4z, you will get e to the 4z times something. Times what?
dz dx.
4
Well, I heard the dz by
dx.
dx. Okay. Is it just dz by dx, or is it 4 dz by dx?
4 dz over dx, just because of the chain rule.
Right. So if you differentiate 4z, don't you get 4 dz by dx's? You see that? That was issue number 1. Right. Uh-oh. If you do a partial derivative of this with respect to x, the answer is not yz. If it was xy on its own, it would be y, right? But it's xyz. So actually, shouldn't we think of that as being f and maybe think of that as being g? Haven't we got two things that have x's in them? One's obviously x, and the z guy has x's in it. So this is going to be a product rule. And if you differentiate x, y, you get y. You leave the other guy alone. Leave this guy alone. And you differentiate z with respect to x, you get dz by dx. So let's see what we got here. We have got 4 e to the 4z dz by dx. We've got yz and xy dz by dx. Remember the goal here? We are being asked to find that guy. So where do you go next?
Well, we have
You'd have to
dz
use
by
the
dx.
algebra.
Well, I got who? Terence, I think we'll pick you. What are you going for, Terence?
All right, so first step, subtract xy dz dx from both sides. Then
Looks good to me. What are you going to do next?
factor out the dz dx.
Looks good.
Then divide both sides by the 4 e to the 4z minus xy.
It takes me longer to write it than it is to see it or to think it. But does that process make sense? Aren't you essentially just solving an equation, right? And you're trying to solve it for dz by dx. Now, this function is symmetric. And because it is symmetric, I don't need to do any work at all. Look at this answer here. I should be able to use it to predict what the other answer will be. Any takers on that one?
X.
How did you know it was?
Over.
Right,
4.
okay. XZ over 4.
4 e to the 4z minus xy or yx.
Or YX, but it's the same thing really, right? Now, someone was going to say, how did I know it was symmetric? Was that your question?
Yeah, that was my question.
Right. Z's don't matter in these questions. But do you know if you switch the X's and Y's, right? Make the X a Y, make the Y an X. Don't you end up with the same thing? Isn't YXZ and XYZ essentially algebraically the same thing? If you can do that, you are symmetric. Right. So if you can switch the X's and Y's, switch places with each other, and the expression is essentially the same, you are looking at symmetric. What that does is, can you imagine the questions where they ask you to find both of them? Isn't it good that you only need to do one and then you can jump to the other one, you know, and save some time? If you can see it, it's good. Now that one is like the ultimate end of horrible. Would you agree? That one had lots of places, you know, you missed a 4, or you didn't realize that e to the 4z, you know, generated this. You thought it just gave you a 0, all sorts of things, or that you missed the product rule on the other side.
Let me guess, that was when you include roots and trig to make us go.
Yeah, square roots and cube roots and anything with trigs in it. Worst case scenario, aren't fractions with square roots in the bottom even worse? Yeah, you just have to be really, really careful when you see messy things like that. The rules don't change, right? What you do is fundamentally the same. The application will catch you. Now, the next group of questions are kind of fun, but I'm only doing them with you. They're just, I like questions like this because they're puzzle questions. They're really just not part of the usual world. We're being asked to find dz, the partial derivatives, right? And the function z is given with a minimal amount of information. All you're told is that z is a function of x plus some other different function g of y, right? So it could be anything. It could be x cubed plus sine y, right? That as an example. That's a very, very general function, isn't it? There's not an awful lot of details. Yet, one of these guys is dz by dx. Right. If you find the partial derivative of this expression with respect to x, which one of these guys is it?
Oh, would it be f prime of x?
You're correct. Tell me why.
Because the g of y is treated like a constant since we're finding the partial derivative with x.
Agreed. And we don't care if the g of y is y cubed minus y all over y squared minus whatever, right? Don't care, because isn't it all just one big ugly number, so its derivative is 0. Yeah. I'll leave you for the second one, but you could probably find out. Now, here's a different world. Z is a function of x plus y. So that means z is like x plus y cubed, the sine of x plus y, right? Things that look like that. E to the x plus y cubed, right? That's the kind of family that it belongs to. Nonetheless, you should be able to figure out which one of these fellas is its derivative.
It would be the f prime of x plus y because we would have a chain rule, wouldn't we?
Yeah, and isn't the derivative of x plus y just 1? Right, I'm going to do one of my own then, and we're going to make your life hard by giving you a few seconds to think about it before I land you in the deep water. I'm going to look at a family of multivariate functions that look like this. Not unlike the one that we just did. And I want you to think for about 30 seconds before you commit to what the derivative partial derivative with respect to x would be and how you might write it. And while you're thinking about it, you may want to give me your last name for attendance. if you've already thought enough about it. Okay. Rosie, I'm putting you in the spot. If you get an idea what that might be.
Okay, so I'm assuming this is going to be something chain rule related. So
Yep.
f prime of x squared plus y squared. And then the power would be,
This bit's right. So finish the chain rule and you're done.
okay. Okay, so the chain rule times the partial derivative with respect to x of x squared.
Okay,
Not quite
which
sure
is?
which is 2x.
Yes.
Not quite sure how to say it.
Oh, well, that's it. Say 2x.
Okay.
And that's it. I mean, I guess I could tidy up, but would you agree that's the answer? Right. Now,
That's
here's
what I
a
got.
perfect. Have a look at this one. Z is f of x, g of y. Suppose I asked you to find, this is for anybody this time, what would that one be?
That would be g prime of y times f of x.
Okay, I agree. Let's put the x and y inside. And let's get an x this time. Any takers for that one?
F prime of xy.
That would be y
Yep.
times f
One.
prime of xy.
I have f prime of xy, and I didn't catch the other bit after that.
Times 1y.
Times 1y. I'll stick it to the front because it looks pretty there. And they're kind of fun. I mean, you're doing partial derivatives, but aren't you doing it for very vague functions, right? Functions that just have a particular shape or combination of how x's and y's interact. And I kind of like questions that do that. So our last one of this type, and we're moving on to something else. Sometimes the simplest are the worst. We're going to do both versions, but let's do this one first. F is a function of x over y. So it could be e to the power of x over y, or x over y to the cubed or something, right? Any takers?
That would be
think I got
1
this
over
one.
y times
Okay,
f times x over y.
Okay, I got it. I think I got this one, and then I think I heard an f primed x over y. I didn't catch the last part, so how would you finish that one?
Multiplied by 1 over y.
Do you agree? Does that look good?
Oh.
Right. Yeah, that would basically it. Now, the one that's probably going to cause you more trouble, because I said the simplest ones can cause the most problems, is that when you differentiate this partial derivative with respect to y, this function here, you have to be careful about it. It's going to start with that. So I'm giving you that for free. And it is a chain rule, but you got to finish it off.
Well, you could rewrite it as x times y to the negative first power, and then it's a lot easier to evaluate that.
And if you
so it
did
just
that, yep, you want to finish it for me?
yeah, it just becomes negative x times y to the negative second power, and then style points it's negative x over y squared.
Right. That makes sense. That's a chain rule, right? Derivative of this times what you get when you differentiate x over y. So there are a bunch of questions. I think the last one finishes at 15. So what have we done today? We've done a couple examples of partial derivatives. Then we did implicit differentiation. We did some of that. Now we did, I guess I'll call these puzzle ones because I can't think of a name for them. Now we're going to move on to multiple partial derivatives. Essentially, we are not just going to find a single partial derivative, but like a double or even a treble partial derivative. Before we get into doing some examples, let me tell you some interesting properties. Suppose you have a function z equals, let's have it in terms of just two variables, x and y. If I ask you to find that, what I'm asking you to do is to find the partial derivative of z with respect to x, and then later on the partial derivative with respect to y. That notation is also going to be called that. And if you remember at the end of last quarter when we dealt with this, would you agree that this notation is much uglier because the order you do it is that way? This to me is much more natural, right? X is first, then whatever the answer is, do it with y's. X is first, then do it with y's. It's quite easy to kind of mix them up. But there's a lovely one, Clairaut's theorem. I think there are 9 there. I don't know how to spell Clairaut. There's Clairaut's theorem. That's definitely not how you spell it, but that's how you pronounce them. French should learn to spell properly. He said that provided your function, right, your original function is continuous, and to them continuous just means, because they're all surfaces, a nice even flowing like English Valley, right? No funny holes and vertical asymptotes, no breakages, right? Nothing weird going on. As long as it's a nice, well-behaved, continuous function, he found out that when you do multiple derivatives, it doesn't matter what order you do them in, you still get the same answer, which is really helpful because if you screw up this notation, won't you still get the right answer? Because Clairaut says it doesn't matter if you do the x first and the y second and the y first and x second, provided the original function is nice and well behaved and continuous. Of course, isn't there a possibility that the function isn't? Can you imagine a simple function like 1 over x minus y? Would you agree that that would have problems every time x and y are the same number? Right. I do not want to try and assume that if you differentiate with respect to x and then y and y with respect to x, that this is guaranteed to always be true. Isn't it going to be a problem if you try and do it to x equals y, for instance? Although Clairaut has an adaptation that says, even if the original function has some horrible pieces to it, right, like a vertical asymptote going on, as long as you don't do it anywhere near that vertical asymptote, this still works. So it's a pretty resilient formula. Which brings me to one of the properties that is very commonly used. If I know the second derivative x then y, isn't it always going to be the same as the second derivative y versus x? So I can kind of save some time. And that's true whether the function is symmetric or not. Okay, so let's do a nice baby question just to get the ball rolling. Let's do x cubed y squared take away x y cubed. Right, nice polynomial. And let's do all the second derivatives. Well, I first have to get that guy. And that's going to get me 3x squared y squared take away y cubed. And if I do a partial derivative now, with respect to y, I get 2x cubed y take away 3x y squared. So far, so good. Now, using that as my building block, can't I now get that second derivative? Which means differentiate this thing now with respect to y, and you get 6x squared y take away 3y squared. And then I'm going to do this one, even though I technically don't need to. And if I differentiate this guy with respect to x, don't you get 6x squared y? And this guy with respect to x, you get 3y squared. Haven't I just shown you that Clairaut's theorem works perfectly fine? Do you see they're both equal? Now, let's do zxx, which basically means differentiate this guy with respect to x again. So that guy gets you 6xy squared, and won't that get you nothing? And if you do a yy, differentiate this guy with respect to y, you get 2x cubed minus 6xy. Do you notice that these aren't even vaguely like each other for the most part? And aren't these not really like each other? Right. So Clairaut's theorem just says that as long as it's the same combination of x's and y's, it doesn't matter what order you do them in, the answer will be the same. It doesn't say that a double x is the same thing as a double y, right? It won't be. And won't a single x not be the same as a single y? But if I did z, x, y, x, y, wouldn't I get the same answer if I did the two x's first and then finish with the two y's? Clairaut would say that would be true, right? That would be doable. Are we good with Clairaut then? He's a useful guy, can help you sometimes. Let's do a second derivative with, I don't know, what shall I put in the second derivative? Let's do a second derivative with some trig in it. Let's do a t, and it's going to be r squared over e to the sine theta, right? Not a lot of trig in it, but some trig. And I want to know the partial derivative, the second partial derivative, that guy. Technically speaking, even though it won't matter in the end because I'll end up with the same result, which variable should I be differentiating with first?
Theta.
Right. Actually, it's theta, but keep trying. 1 and 2, right? So, partial derivative with respect to theta. Well, that guy doesn't matter. If you differentiate e to the sine theta, you do get e to the sine theta. It is a chain rule, so you finish with the cosine theta. And I would probably rewrite it for style points like that. So far, so good. Now, I'm now going to get the second derivative, this one, which means I'm going to differentiate this with respect to r, which is a lot less work. Because basically all I need to do is differentiate the r squared. If they went and asked us to find all possible second derivatives, wouldn't I be able to use this answer and that answer together because they're the same? If I wanted to do that guy, when I differentiate this with respect to r, which would be 2r e to the sine theta, and then just differentiate that again with respect to r, and I'd get a very easy answer, right? Not a lot of work. On the other hand, if I wanted to do the second derivative with respect to thetas both times, won't you use this as your starting point? But can you see how ugly that guy is going to be to differentiate with respect to theta? Aren't you going to have to do a product rule and be careful because there's some chain rules in there later? Right, so one might be trivial and the other would, oh God, this is going to take forever, right? Any questions? Are we good? Multiple derivatives? Anything? Okay. Oh, I now know how to spell Clairaut because it's on the thing I'm looking at. C-L-A-I-R. Actually, I was pretty close the first time until I gave up. There it is. So if you
It
want to
still
spell,
sounds like cannibal breakfast cereal.
does it? It's not very, yeah, it's not very pretty.
I thought for sure it would end in it like an AUX or something.
Yeah, it sounds, French words like Bordeaux or something makes you think that, don't it? Not saying that one ends with it.
Why do we just accept French spelling? Or why don't we just change it to make more sense? Like,
What, change their way of spelling it to our way of spelling it?
well, we're
As
spelling it
English-speaking
French way now,
people.
which is like admitting defeat.
No, I think what we should do is just tell everybody in the world to speak British.
As English-speaking people, we fought lots of wars with France. We should just accept that we won most of them.
Okay then.
I am not calling Worcester Worcester for anybody.
Yeah, I hear you. Okay, that was our kind of foray into multiple partial derivatives. It's really doing the same thing but doing it twice or three times. So as long as you look at it like that, you're fine. So what we're now going to do is finish off by looking at solving a very interesting equation called Laplace equation. This guy, unfortunately, he's French, I believe, since we're picking on French. The French turned out a lot of really good mathematicians. They had a heyday, I think it was in the 1700s into the 1800s, where, Laplace, let's see, Raynaud, I can't think of any, but there were tons of them. It'll come to me later. The Cartesian coordinate system, for instance, was created through a French mathematician's thoughts. This here is called Laplace's equation. It is an interesting equation because basically there's a function u, which is actually some kind of function of x and y, and there are many different functions that solve that differential equation. It's a partial differential equation. You see, it's a partial differentiation with respect to x plus a partial differential equation with respect to 0. And the solutions to this pop up in wave theory, heat transfer in particular. And so if you can solve a Laplace equation, you very often are, it's the solution to some physical problem. And what you're being given here is possible solutions. So there are lots of choices. So I'm looking at 6 choices here. Since you can't see them, I'm calling them 1 to 6. I'm going to pick one as an example, and you're going to tell me which number to pick. So this is question 19 if you're interested. So which one shall I pick to test? Is it a solution to the Laplace's equation? Pick a number, 1 to 6.
3.
3 gets the job. 3 is x squared plus y squared. Okay. Now, how do I test that this is or is not a solution? Well, I simply just find that guy and then his second derivative. So, gotcha. And then I find this guy and his second derivative. And then I check, does it satisfy that? Well, unfortunately, no. But can you trust me that that does? Can you imagine I did this? This would solve that. Because what you would get is 2 take away 2. And have fun looking up Laplace. He's very interesting result. Now, the next puzzle, version of question 20, is imagine a plate or a surface, and the temperature at position XY is given by 50 over 2 plus x squared plus y squared. This is not as unreasonable as it seems. Can you imagine you have a rectangular or circular plate and you have the origin here. And the origin is where the heat, right, where the Bunsen burner or the jet engine or whatever it is on it. If you looked at a snapshot in time, would it seem reasonable that you would have bands of hot getting less heat, less heat, less heat as it dissipates to the edge? And this function here is representing the temperature at any given point x and y. Right? So it's basically a heat transfer equation. It might actually solve Laplace's equation. I'm not going to say it does because I haven't checked. So we are being asked to find, let's see, find the rate of change in temperature with respect to the distance. So we're being asked to find that guy at this point, and it's going to be in the x direction. So can you imagine that you put in your x-axis and you put in your y-axis, and you had the 0.13, which is probably about here, and you're traveling in that direction. What is the rate of change, right? How's the temperature changing as you travel to the right, for instance, in the x direction? So I'm going to find the partial derivative with respect to x, and then I'll evaluate it at 1,3. So if I'm going to differentiate this guy, I would strongly suggest, this is just me, that you rewrite it like that. Now, could I leave it as a fraction and do a quotient rule? The answer is yes. Why do I choose not to? Because I tend to screw it up. Because some of those derivatives are zero and I forget that they're zero and I have answer that's not there. So if I do it like this, it just becomes a chain rule. So multiply by the power, reduce the power by 1, and then differentiate what's inside with respect to x, and then make it look pretty. Are you comfortable about that as being the answer? Right, came out pretty quickly. Now, if you want to know what the rate of change in temperature at this point traveling in the x direction is, just negative 100 times 1 all over 2 plus 1 squared plus 3 squared squared. So it's negative 100 over 13 squared, which is neg 169. So whatever negative 100 and over 169. The fact that that's negative, what's that telling me about the
Is that
temperature
13
passage of
squared or 12
9 to
squared?
12 squared? Can't count. Negative 100 over 144. I guess I should simplify it. It's bugging me if I don't. Okay, 2536. Why is this answer negative? What's that telling us about as you travel from here to the right? It's negative. The rate of change is negative. What's that telling us?
Temperature is going down.
Yeah. Does that make sense? At the middle, it's hot, as if you travel away, it gets cooler. Isn't that really all it's saying? Right. Now, I don't want to do that guy from scratch, but I know what the answer is anyway, don't we? Is this function symmetric? If a function is symmetric, can't you predict the other answer without having to do it? And you use this guy to predict it. Any volunteers for what it would be then?
It'd pretty much be the same, except for instead of it being negative 100x, it'd be negative 100y.
Agreed. And couldn't you also plug 1,3 into that and you probably get a slightly different answer? I think the difference in the answer is that it would be 3 times as big. So it would end up being negative 75 over 36. So this piece of metal is not cooling equally, isn't it? Cooling down a lot more as you go north-south and less east-west. Right? Well, the only way I could think of that happening in real life is that maybe the plate with a heat source in the center, maybe the plate is not the same thickness, right? So as you go on the y-axis, it gets thicker, and so thicker material, dissipates the heat more or whatever, right? That would be my goal for this one. And the last question, I'm only going to give you the talk to it because the electrical engineers amongst you already know who this guy is. Agreed? Does any of you, who are you looking at here? Come on, the electrical guys, tell the rest of us what you're looking at here.
Resistance in parallel.
Right, so
Yeah,
you get three
it's a bunch of
resistors. Right, so you've got resistor, 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 I believe. Does it look something like that? I'm not great at drawing pictures. Is that parallel?
Attach the lines that you just attached to the sides, attach them on the top and the bottom.
Okay. Does that work?
No, you want that other line to either, like, I would have them come vertically, like from top to bottom.
Okay, I'm giving up. It's parallel.
That would work. That would work.
As long as you have one wire connected to the bottom set and one wire connected to the top set, then
Everybody's
Think
happy.
about it like 3 roads that go to the same place.
How about that?
Yeah.
Right, third time lucky. Right, so you're connecting them, and this is the relationship. So if someone asked you to find the rate of change of this system with respect to this one, in other words, can you imagine you made these two fixed values, but you had a little variable resistor guy, so you could slide it and make it more or less resistance? What would be the rate of change of the overall system? Now, you can imagine that might be a helpful thing to calculate. The math of that is deceptively ugly because it's implicit differentiation. I wasn't going to do this, but I feel I need to now because not everybody knows what the heck's going on. This guy R is considered a function of R1, right? It's implicit differentiation. When you differentiate 1 over R, you get -1 over R squared times dr by dr1. Are you happy about that? Guy gets you this. That's the implicit differentiation. That guy gets you nothing. That guy gets you nothing. But isn't the derivative of this guy -1? And what did that? Yeah, -1 over R1 squared. So I have -1 over R1. This fella is -1 over R1 squared. If I multiply both sides by -1 and then multiply both sides by R, here is, whoops, the remarkable result. The change in resistance of this system with respect to the resistor R1 is, right, the rate of change is just 1 over the resistance of R1. Does that make sense to the people who know what the heck is going on here?
This is pretty much exactly how we control the speed motors turn. Well, I mean, it's not the way we do it in the 21st century.
But how
this
you
is the
could
way we
have
did it
back in the day.
19th century, yeah.
So do you see, I know, as you can tell, I know absolutely nothing virtually about this, but doesn't the math doesn't care that I don't know anything about it. As long as I know the process, I can calculate it for, you could give me the ugliest looking system, right? Just tell me who the formula is, tell me how many variables you've got, and tell me what you want me to find the rate of change of, in this case, this one. We can do the math and we can come up with an answer, and then I'll say, yeah, okay, this is the answer. You tell me what it means. That is us. Sorry for keeping you a little bit longer, but it was kind of nice to do that because that is the last question essentially, right? And so tomorrow we're starting a new section where we're going to be looking at the chain rule.